So, enzymes and energies, the main topic. Before we get too deep into that, though, there's two things that I should have talked about in the last unit that I skipped over. So I want to go back and hit those first. Well, I said I wanted to. There we go. First of all, the nitrogen cycle we have talked about off and on all semester. But from reading the essay questions, I saw that a lot of you did not understand it very well. So, re-talking about that again. There's a lot of nitrogen on Earth, but most of it is locked up where? In the air, as N2. N2 is held together by what kind of bond? A triple covalent bond. Makes it very difficult to break. And if we can't break those two ends together, if we can't break the two ends apart, can we use that nitrogen? No. There's almost nothing on Earth that can break that bond. Very few things that can. Most of the things that can are where? They're in the ground, usually living on the roots of plants in some kind of symbiotic relationship, and the organisms that can do it tend to be what kind of organisms? Bacteria. So what we can see in this diagram is that we've got some atmospheric nitrogen, N2, and that what's happening to that N2 is that the bacteria are grabbing onto it and taking it and converting it into kinds of chemicals that living things can use. That process of taking the N2 and converting it into a form that we can use and plants can use is called what? Nitrogen fixation. And you can see that down here. The nitrogen fixation process, during that process, bacteria convert N2 into two main things. Ammonium ion, which is what? NH4 plus, and eventually to nitrate, which is NO3 minus. So in general, nitrogen fixation is the taking of atmospheric nitrogen N2 by bacteria and converting it into a form useful for plants and animals, which is either ammonium ion or nitrate ion. So that gets used by the plants. Plants pull that in from the soil or from their symbiotic bacteria. That helps them grow. Why do plants need, why do animals need nitrogen? Nitrogenous bases of nucleic acids, DNA, RNA, ATP, and also the amino groups of amino acids, proteins. So we've got to have nitrogen. We've got to have a lot of nitrogen. Oftentimes, nitrogen is what we call a limiting factor. There's a question about this on move number 7. What is a limiting factor? It controls the number of organisms. Like in a pine, for example. Typically in a pine, there's not a lot of nitrogen or phosphorus, which means there can't be a lot of what? Things that need nitrogen and phosphorus. It limits the number of things. But if all of a sudden there's a lot of nitrogen and a lot of phosphorus, what happens real fast to population sizes? So you grow. It's a nutrient that things have to live. It limits the population size of those organisms.
So limiting factor is?
It's some kind of nutrient that typically is scarce, and therefore it limits the size of a population. Again?
Water and shelter.
Those could be limiting factors. All those things could be. One other thing I'll mention here about the nitrogen cycle, actually two other things. There are bacteria in the soil called denitrifying bacteria. This is called a cycle for a reason, because what ends up happening eventually to that ammonium and nitrate from the soil? It goes back to being N2. It's a cycle, it's a circle. So nitrogen fixing bacteria convert N2 into ammonium and nitrate. Denitrifying bacteria go the opposite way. They take nitrate and ammonium and turn them back into what? N2. So it's a cycle. It's a circle. how have we messed as humans? How have we messed with this cycle? What have we done to this cycle? We learned how to make what? Artificial fertilizers, which are essentially chemicals loaded with what? What's the name for most fertilizers that you would go buy at Home Depot in the bag? What's the bag say on it? Yeah, well it does. But what else does it say? What's the chemical name on the bag? Ammonium nitrate. Both. Most fertilizers are ammonium nitrate. We pour that fertilizer all over fields, right? And all of a sudden, what's not there? If we poured ammonium nitrate on the field, what's not in the soil? What's not going on anymore? It's not, nitrogen is not a what? If we just poured it all over the soil, nitrogen is now not what? It's not a limiting factor, which means the plants can grow more numerous and can grow what? Why farmers put fertilizer on the field? Make them grow bigger, stronger, faster. But the problem with that is a lot of that nitrogen that we pour on fields doesn't stay on the fields. It ends up running off into what? Water. And what does that cause to happen in the water that it ran off into? What starts to grow like crazy in the water? Algae. And we get what are called algal blooms, and that causes problems. If you drive up toward like Scottsboro or Gunnersville, in parts of Scottsboro and Gunnersville, you see it covered with algae, right? I'm going to tell you the reason most of that there is because of farmers. Farmers who have put fertilizer on their fields, and a lot of that fertilizer ends up in that lake or that pond, and that causes algae to grow like crazy. Yes, and we'll get to that later. It's called eutrophication. We'll get to that. Another thing that can cause that is subdivisions near the body of water. How would subdivisions near a body of water cause that to happen? Maybe, but more than that. Most people in rural areas have septic tanks, right? Which means when you go to the bathroom, you flush the toilet, it just goes out in your yard, right? In a big hole. And there are pipes that lead away from that big hole out into your yard, right? A lot of that poop ends up where? And running through the ground, and it ends up in the rivers or in the ponds or in the streams. Who's loaded with what? It's loaded with nitrogen and phosphorus. So that's why farmers, a lot of times instead of buying artificial fertilizer, they'll pour chicken poop or cow poop all over their field, right? Well, we don't keep it all. If we have extra, we scoop that out. No, we can only store a certain amount. Constantly resupply. Yep. Yeah, it's everywhere. Two other quick things. That acronym up there, SHNOPS. What is that? Yeah, those are the 6 elements most important to life. The 6 elements most important to life. Carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. By far, those 6 elements are the most common things found in living organisms. The most common elements for life. SHNOPS. Well, it's in proteins. It's an important part of proteins. Disulfide lines. That's about it. That's the only thing I know of. But since proteins are everywhere, it's pretty much everywhere.
What's the P, phosphorus?
Phosphorus. Yeah.
In order of what we eat together.
No. What is the most common element in your body by far? Hydrogen. 70% of your body is water, right? For every 1 water molecule, there's what? 2 hydrogens. What do we know about organic molecules? They all have a lot of hydrogen too. Sometimes, most of the time, more hydrogen than what? Than carbon, at least in terms of numbers. Now, by weight, probably what is the most common element in your body? Not by number, but by weight. Nope. Oxygen. Okay. Because 70% of your body is what? Water. Water is how many times heavier, or oxygen is how many times heavier than hydrogen? It's 16 times heavier. And organic molecules, most of them have a lot of oxygen too, right? So it's everywhere. Of these up here, probably the one that's the least common, sulfur. And then probably phosphorus. And then probably nitrogen. And then probably carbon. And then oxygen, and then hydrogen, if we're talking about simple numbers of atoms. All right, one other thing that we should have talked about during the last unit that we didn't are buffers. What's a buffer? Well, it can mean that. It's a cushion against what? It's a cushion against changes in pH. A buffer is a chemical that helps to keep the pH of your body from changing very much. That's pretty important. Because if the pH of your body changes, what happens? Your proteins start to what? Denature, and you die quickly. Think about it. Pretty much all of you probably drink Coke or some kind of soda. What's the pH of that Coke or soda? It's low. It's probably 3 or so. It's pretty acidic. I drink over a liter of it a day. How much blood do I have?
Why you drink so much?
Well, a liter's really not a crazy amount. I mean, a 20-ounce drink is not much less than a liter, right? A liter's not a big unit.
I was thinking about
You're talking about 2 liters.
2 liters.
Yeah. But anyway, how much blood does an average sized guy have? Somewhere around 5 liters. I'm drinking at least a liter of soda a day. The pH of my blood should be what? You should know this number. What should the pH of your blood be? A little bit higher. A little bit lower. Should be 7.35. That's a number you should know. That's the pH of your blood and your body fluids. And if it changes much away from that, 7.35, you will die very quickly. Slightly basic. Now here's the thing. If I took 5 liters of water, which I'm going to make be my blood in this analogy, 5 liters of water, and I stuck a pH meter in there, it's going to say 7, right? And I poured in a liter of Coke. What's going to happen to that pH? It's going to go down, like way below 7, right? But that doesn't happen in my body. I could drink 5 liters of Coke, and the pH of my blood is not going to change very much. Well, there's several ways. One of the reasons that your body helps to keep the pH constant is with buffers, and we'll explain what a buffer, how it works in a second. Another way is through urine. If you drink too much Coke, your kidneys are made to filter out what? They filter out a lot of ways, but in relation to this, what do you need to get rid of if your blood's too acidic? What makes it acidic, guys? What makes acids be acids? Hydrogen ions, okay? So your kidneys will filter out hydrogen ions and you urinate them out. If you drink too much Coke, your urine becomes what? It becomes acidic. And that's why it sometimes burns, okay?
That's STD.
Maybe that too. Okay? Let's hope it's not that. Okay? Let's hope it's Coke and not syphilis. Okay? But regardless, it could be that. It could be. Anyway, let's talk about buffers for a minute. A buffer is a chemical system. It's a chemical system in your body that helps to resist changes in pH. The most important buffer system in your body is called the carbonic acid bicarbonate ion buffer system. What's carbonic acid? What's the formula for it? Help me out. H2CO3. Carbonic acid. That's the stuff that makes Coke be Coke, right? Carbonated water. That's water plus carbon dioxide, right? Water plus carbon dioxide. Carbonic acid. First of all, why do I have arrows going both ways here? Not so much equilibrium. It's called a reversible reaction. It can go either way. When this stuff breaks up, ionizes, it breaks up into, it's an acid, so what's it always going to give off? Hydrogen. We're just going to write it as hydrogen. And what would be left? What ion would be left? Hence the name of the buffer system. Bicarbonate, which is H, CO3, minus 1. That's bicarbonate ion. Now, there's an important idea in chemistry. That's one of the most important ideas in chemistry. You probably didn't talk about it in Chemistry 1, though. You probably don't get there. There's this idea called Le Chatelier's principle. Pretty important idea in chemistry. Le Chatelier's principle. Wait a minute, let's see. Le Chatelier's. It's a French guy. Le Chatelier's principle. That's an L right there. And basically, the idea of Le Chatelier's principle is this. If you have a system at equilibrium, and something messes with that system, what does that system want to do? It wants to find a way to get back to equilibrium. It wants, once nature gets to equilibrium, it wants to stay there, right? And if it gets messed with, it tries to get back. That's Le Chatelier's principle. If you have a system at equilibrium, and something messes with that system, it's going to try to get back to equilibrium. For example, let's use this equation up here to talk about Le Chatelier's principle. Let's say your body, the pH of your body right now is at 7.35. It's where it needs to be. All of a sudden, you drink a big 2-liter Coke. You're really thirsty, okay? You drink a 2-liter Coke. What did you just inundate your body with? Acid, and therefore, which one of these things? Which one of these things did you completely... No. H plus, okay? You might have put some carbonic acid in there. The thing about carbonic acid is it's giving off H plus, right? When you drink something acidic, maybe lemon juice, vinegar, okay, Coke, whatever it might be, you're increasing this. Well, what does that do to the equilibrium? It messes it up. Because now there's more of those than there ought to be floating through the blood. Your body doesn't want that. So you increased it by drinking Coke. What's your body going to do? If you increased it, your body wants to decrease it. And the way it decreases it is these two reactions. The one going left to right and the one going right to left. What can it change about those two reactions? What can it change about this way compared to this way? It can change the speed. If all of a sudden there's too much of this H plus in your body speeds up this reaction. If we're going this way, what's happening? What's your body doing to H plus? We're going right to left. It's taking it away and storing it as this, right? And then what does it do to this reaction right here? It slows it down so that less and less H plus is being what? What's this way doing, left or right? It's releasing it. So it slows down the release of H plus, speeds up what? The storing of H plus. So that the H plus levels drop back down to where they need to be. Let's say that Jonathan said a dirty word in front of his mom. Okay? And Jonathan's mom said, "Jonathan, we don't talk like that in our house." So she pulls out an old-fashioned bar of soap. which was made out of what? Lye. Lye's a not so fancy word for what? Sodium what? Hydroxide, a base. Sticks that in Jonathan's mouth and says, chew on this. Okay? So she washes his mouth out with base. Jonathan swallows some of that. That sodium hydroxide that he swallows does what to the amount of H pluses in his blood? What does hydroxide do to hydrogen ions? It takes it away, right? So all of a sudden, the amount of H plus starts to drop in Jonathan's blood. That's not a good thing, right? If H plus goes down, what happens to pH? It goes up, right? Less H plus means pH goes up. So that's just as bad as the other way, right? Either way, your pH changing up or down is bad. So Jonathan's body says, whoa, H plus is too low. I better what? I better make it go back up. And the way it makes it go back up is it speeds up this reaction and does what to this reaction? Slows it down. That's the way buffers work. Does that make sense? It's all based on this idea of Le Chatelier's principle. If you have a system at equilibrium and something messes with that equilibrium, nature's going to try its hardest to get back to equilibrium. Nature wants to stay there. Yeah, let's move on to our main stuff. All right, this chapter is about energy and enzymes. Energy and enzymes, that's the whole chapter. First big thing that we need to mention, energy is the ability to what? If you look up the definition of energy, it's the ability to do work. Ability to do work. Now in physics, work has a particular mathematical definition. Anybody know the physics definition of work? Like in an equation, what's work? In physics, we're going to see that work is equal to force times what? Distance. Which means to do work, something better be what? Moving. Work implies movement, moving something. So we might also define energy as the ability to make things move. Okay? Ability to do work or the ability to make things move. However you think about it, all the energy on Earth, in one way or another, comes from the sun. It's the ultimate source of all Earth's energy. With one exception that I can think of. What would that one exception be? Yeah, that's probably true. That's not what I was thinking. That is true. Where on Earth might you find some energy that didn't come from the sun? The stuff coming from the core of the Earth, right? Volcanic stuff. Okay? That's coming from friction and radiation and all that stuff together, right? But in terms of biology, is that kind of stuff really very important? Not so much. Okay? In terms of biology, all our energy comes from the sun. It's the ultimate source of energy. Now, you guys all have heard about kinetic and potential and those kinds of energy. When we talk about kinetic energy, we're talking about energy of what? Movement. It's the energy of moving things. What kind of energy that we've talked about in here several times already is a form of kinetic energy? Well, diffusion is not really a form of energy, but what causes diffusion? Which is caused by what kind of energy? Thermal, heat. Thermal energy is a type of kinetic energy. It's about motion. Most of what we're going to talk about in here, though, is potential energy. If Camille had been misbehaving in class, because she is really loud, right? If Camille had been misbehaving in class, and I wanted to try a new discipline technique, so I got something really heavy, and I said, Camille, the worse you are, the higher I'm going to lift this thing above your head. Okay? And eventually I'm just going to let it go. Okay? I'd go to jail after I did it. But if I did that, okay? as I'm lifting this thing above Camille's head, I am adding what to it? I'm adding energy to it. We call that kind of energy due to something's position. We call that gravitational potential energy. Gravitation, because what's going to pull it down eventually when I let it go? Gravity. The higher something is above the ground, the more gravitational potential energy it has.
So what does this do with height? It's gravitational.
Right. If it has to do with height, it's gravitational potential energy. It's energy that's, potential in general means energy that's what? Stored. Stored. That guy who jumped out of that balloon several thousand feet above the earth the other day, he had a whole lot of gravitational potential energy, right? So much that when he came out of that balloon, how fast did he end up going? 800 miles per hour, falling. All he had on was basically a space suit. He fell 800 miles per hour because of gravity. Faster than the speed of sound. He pulled his parachute, landed on his feet, and walked away. Had been falling 800 something miles per hour. That's pretty incredible. It's pretty stupid in my estimation. Kind of cool. I wouldn't do it.
I parachute even stopped it from falling 800 miles per hour.
Well, he had to pull it a long way from the ground.
That would have been a hard
Yeah, it probably.
Oh, I'm sure he got jerked when he pulled it, yeah.
The parachute.
Then he wouldn't have made it. Okay? I'm sure his parachute was specifically designed to handle that. I mean, it would have to be strong.
Couldn't just be a trash bag.
No. No. Trash bag wouldn't handle that.
Can't be trash bag.
Regardless, gravitational potential energy in this class, we're not going to talk too much about. That's physics thing. That's actually tomorrow's topic in physics. The kind of potential energy we're going to talk about in here mostly is chemical potential energy. Energy stored in chemicals. And we know from previous discussions, in a chemical, where's most energy stored? In the bonds. What kind of chemicals are the best at storing energy? Which kinds of chemicals are the best at storing energy in living things? Fats, lipids. ATP is really good at it too, but it's more of a short-term thing, right? Lipids are good long-term energy storage molecules. Now, we also need to talk about some important laws. We mentioned one of these just a second ago. The first law of thermodynamics. It's also sometimes called the law of conservation of energy. Two names for the same thing. It's one of the most basic ideas in all sciences. And we said it's the idea that you can't what? You can't create energy. You can't destroy it. You can only what? Change it from one form of energy to another form of energy. You can transform it. You can convert it from one form to another. You can't create. You can't destroy energy, but you can convert it from one form to another.
And that's the first law.
That's the first law of thermodynamics.
What is that also called?
The law of conservation of energy. You can convert it from one form to another. The amount of energy in the universe today is the same as the amount of energy in the universe at the beginning. Correct? Those forms of energy have been changed to different forms of energy, but the total amount of energy is finite. Finite means what? Limited. Limited. Okay? It's not infinite. It's finite is the opposite of infinite, right? It's limited. There's only a certain amount. All right, now the second law of thermodynamics is going to be really important in this chapter. And it's probably the most confusing thing in this unit. I'll give you a really basic idea of what it is here first. Every time a living thing uses energy, when you eat food, for example, some of the energy in that food is used to make you do whatever it is you do. But a lot of that energy is given off as what? Heat, waste. Once heat is given off, can we in biology recapture that heat and use it to do useful things with ever again? No. Once energy is converted to heat, it's kind of useless in biology. We can't get it back. So the idea of the second law of thermodynamics is about this concept called entropy. What's entropy? Disorder, chaos. And basically the second law of thermodynamics says this, that in nature, entropy is constantly what? Increasing. The universe is becoming more and more chaotic, disordered, disorganized. In nature, entropy is constantly increasing. Now that seems sort of, and there's a question in your Moodle assignment about what I'm about to mention here. That seems counterintuitive. Because if you think about evolution, right? What's happened with evolution on Earth? What do we supposedly start out as? Single-celled bacteria, and that things have become more and more organized and ordered, right? But that's only one piece of the picture. Every time something uses energy, what do we say happens to that energy? Some of it. It's given off as heat, never able to be what? Reused again. So the amount of usable energy is what? Constantly decreasing. That's entropy. Energy is being converted to a form that we can't get back. We can't use. Our energy sources are finite. Entropy is increasing. The amount of stored usable energy decreasing. That's the second law of thermodynamics.
Increasing.
Entropy. Entropy is constantly increasing. Because every time stored energy is used, some of that energy is given off as waste what? Heat. Can't use heat anymore. Heat's gone. The heat that your body's giving off right now is ultimately going to end up where? Where's it going to end up? The heat that we're all giving off right now, where's it going to end up? Somewhere out in space. It's going to diffuse its way out of the atmosphere into space somewhere, never to be able to be used again. Okay? It's gone. We're taking organized food energy and we're converting it into heat energy that we can't use anymore. That's the second law of thermodynamics.
So entropy is constantly increasing. So every time energy is used.
Some of it, the energy is given off as waste heat. Again, let's state that again. Second law of thermodynamics basically says that the amount of entropy in the universe is constantly increasing because every time stored energy is used, some of that energy is given off as waste heat. And that can never be used again. It's gone. Now here's another thing, another way to think about the second law of thermodynamics. You're pretty organized. Your body's very organized, right? According to the second law of thermodynamics, what does your body constantly have to do to stay organized? You have to continually add energy to stay organized. That's another way of thinking about the second law of thermodynamics. To stay organized, you have to have a constant source of energy in order to overcome what? Entropy, disorder. To stay organized, there has to be a constant source of energy to overcome disorder.
So basically saying that brain has energy.
Eventually. But if your body does not have energy, what happens to it? You fall apart. You become disorganized. To stay organized, you have to add energy. Yeah.
That's like what people don't have that much energy.
No, not so much. So another way to state the second law of thermodynamics: energy must be added to maintain order or homeostasis. Source of energy. Constant source of energy. All right, I want to look at one more thing before we go. That's this slide. We talked about the two sources of energy, potential and chemical, two types of energy. To make all these macromolecules that we're made up of, proteins, the nucleic acids, carbohydrates, lipids, it involves energy. Dehydration synthesis is another word for what? What did we usually call dehydration synthesis? Condensation. Takes away water from something, right? Condensation reactions tend to put things together, right? They're building reactions. To make the bonds, what has to happen with energy? To put two things together, what do you have to do? You have to put energy in. On the other hand, hydrolysis reactions break bonds. So what do they tend to do with energy? They tend to give it off. Condensation or dehydration reactions put things together. To put these two pins together, in my analogy here, I have to add energy. On the other hand, when chemical bonds get broken during hydrolysis reactions, they tend to release energy. That makes sense?
Shouldn't it kind of like this cancel each other because when the condensation reactions when they come together, they're using energy, meaning they come apart and just releasing the same energy they use.
But it's sort of like using batteries. You might charge the battery from your wall socket, but then you might use the battery to make the light bulb come on. You're taking energy from one place and using it somewhere else. So you take energy from food, food loses the energy, but you gain that energy. See what I'm saying? It makes you do stuff. So it's moving the energy from one place to another. Yeah.
That's why, like, sometimes you get this part you call it bake something, you call it like hot. So, like,
Yeah, because it's generating heat. Generating heat. All right, that's probably a good place to stop. Remember that for